20-1s. Welcome to Chapter 7, Absolute Values and Reciprocal Functions. I have to be honest with you, it's a bit of a chunky chapter because with absolute values, it's not a lot of lessons. There's only going to be 2 lessons. Today's, which is really going to focus on something called Piecewise, which is going to deal with the domain of absolute functions. Different. Not a lot of calculations, but some thinking. And then, next lesson, we're going to solve absolute value equations. And that process, we've been solving all kinds of different situations. Today, you got to think a little bit about this piecewise. Not a lot of calculations. Next lesson with the solving, a little bit more calculations, but arguably not as much thinking. So, from there, we're going to go to reciprocal functions, which are totally unique again onto themselves. But they're unique because of some different reasons, and it's going to be about graphing. So, different kind of unit. So here we go. Let's get started. Absolute values, page 2. Absolute values tells us that for any real number, which is what we deal with in high school, is the absolute value is always the positive of the number. Doesn't matter if it's a positive or a negative, which seems kind of weird. But that tells us, and we see absolutes, they're in straight brackets. So if I had the absolute of positive 7, well, the absolute value of positive 7 is positive 7 because the absolute signs make everything positive. But that means if I had the absolute of negative 7, well, absolute value signs take every real number and make it the positive. It's a little bit goofy, but the reason why, if I have the absolute of A, if A is greater than or equal to 0, well then it's just going to be that value. Absolute of A will be A if A is positive. So like it says, here you go. If I have the absolute of 7, well that equals 7 because our A is greater than 0. But what an absolute value sign is doing is that the absolute of a negative, something less than 0, what it's doing is it's getting the negative of it. So it's saying we want, because it's a negative value, we want the negative of that negative value. That's kind of what an absolute's doing. It's saying, and it recognizes, hey, it's a negative value inside of these absolutes, so we want the negative of that negative value, which gives us the positive. Kind of quirky, but mathematicians and the absolute signs say anytime if I have a negative value inside the absolutes are saying, you want to know something? We therefore want the negative of that negative, which means we get the positive of it. That's kind of the math that's happening. Another way to think of it, and becomes quite popular, is if I have a number line, which is always going positive to the right, negative to the left. An absolute is the distance from 0. I don't care which direction it's going. That doesn't matter. So that's another way people use to describe absolutes. What's the distance of that line? Well, that line has a distance of 3. It's 3 away from 0. Well, what's the distance of that line? Well, that line has an absolute distance of 4 because it recognizes, yes, it's a negative direction, but we don't care about that. The distance, the absolute distance, is simply 4. We don't care that it's a negative direction. So that's kind of what an absolute value is all about. So we can do calculations with absolute values. Now, this isn't overly complicated, but you have to be very careful and focused. Absolute values in expressions or calculations, I guess we could sort of say when it's involved with bed mass, the absolute acts like curved brackets in normal bed mass. What do curved brackets in normal bed mass tell us? Well, it tells us to perform the calculation inside first. So we're always going to calculate inside the absolute first. It also tells us that a value beside the absolute brackets needs to be multiplied by that value. So those are the two key things about absolute value signs when we're calculating. So let's take a look. Page 3, if I want just the absolute of 3, well, that's just 3. It's going to stay positive. The absolute of negative 7 is going to be 7. The absolute of 9 is going to be 9. The absolute of negative 12 is going to be positive 12. So that's what an absolute sign is doing, just telling us that number in the absolute has to be its positive form. But here's where we get to calculations. So this first one tells us we want the absolute of 4, take away the absolute of negative 6. Well, there's no calculations in the brackets, but I need to, before I do a calculation outside the absolutes, is get the absolute value. So the absolute of 4 is 4. And we want to subtract that from the absolute of negative 6. Well, the absolute of negative 6 is positive 6. So this question is saying 4, take away positive 6. Our answer is negative 2. It's okay to get a negative answer because we don't have the whole thing in absolute brackets, but our calculation, 4 subtract positive 6 gives us negative 2. We still follow bed mass. So this second question, we could kind of think of it like we have curved brackets. What do the round curved brackets tell us? Do that first. So let's do that first. 5 minus 3, 2 minus 7 is negative 5. Well, what would, after I've done that, what would my next step be? I would need to multiply. So I have to multiply, but I need to multiply 3 by the absolute. So that's where I have to now change. It's going to be 5 minus 3 times the absolute of negative 5 is positive 5. So this will become 5 minus 15, which is negative 10. So we have to break it down into these steps following bed mass, but when we're left with an absolute with just a single number, we need to convert it to the absolute value. The next one, lots going on. In this case, all we need to know is that these are inside the brackets. And when they're inside the brackets, everything needs to be done first, and we're simply going to finish with something inside brackets. So that's all I have to worry about with this one. I just want to do order of ops inside the brackets. So I have negative 2, bracket, negative 2 squared, minus 7 plus 6. I'm not worried about the absolutes yet. They're on the outside. I need to do everything inside first. So negative 2 squared is positive 4. Negative 2 times positive 4 is negative 8. Still have subtract 7. Still have plus 6. Negative 8 plus negative 7 or subtract 7 is negative 15. Negative 15 plus 6 leaves us with negative 9. But all of that's inside the absolutes. Absolutes, did everything inside. Now I have absolute of negative 9. Finish it off. Absolute of any value is the positive form of it. There you go. Next one, negative 12 plus 8. Do what's inside the absolute value first. Negative 12 plus 8 We still have the absolutes of -4, but the absolute -4 becomes the positive of it. And the last one, kind of similar to the one we'd done previous, we just need to do all the calculations underneath first. Order of ops, exponents first, so we have the absolute, 12 times -3 plus 25, because I did the exponent first. Multiply, absolute of -36 plus 25. Finish off inside the brackets, the absolute brackets, -36 plus a positive 25 leaves us with a -11 in absolutes, which tells us our answer is the positive of it. So, calculation with absolutes, bed mass, but understand it converts to its opposite. Now we have some questions about where do absolute values actually come into play. Well, they do come into play, to be honest with you, but it depends upon what a question's talking about. So page 4, the first question, I've summarized it here. You can read it. It talks about the stock market. A stock starts at $13.55. It drops to $12.70. It increases to $14.05. Finishes at $13.85. Now, what's important is this question doesn't ask what the final value of the stock is, because the final value of the stock is different than total change. If I want to know total change, I don't care if it's going up or down or whatever. I just want the total of every dollar value that's occurred. Well, if I want to know the change of things, it's always what do you finish with, subtract what you started with. So the first change was from $13.55 to $12.70. So what was the change? Well, finished at $12.70, subtract where it started, but we want the absolute of that. Because this, if I just take a look, $13.55 to $12.70, that's a drop. But I don't care that it dropped. I don't worry about the direction of what happened. I just want to know the total amount. So I want the absolute of the 85 cents there. But what happened next? Well, the total change would be the next change that occurred. And it went from $12.70 to $14.05. So it went up. But I don't care, to be honest, that it went up. I just want the total of it. Finished at $14.05, and it started at the $12.70 for that second change. So that would be a change of $1.35 positive. But I just want to know that it's the positive because I want total change. And the last change that occurred is it went from the $14.05 and finished at $13.85. Well, we can see that that's another decrease. But I don't care that it was a decrease because I want just the amount of the change, which is why it's an absolute. It finished at $13.85 from the $14.05, which was a change of -20 cents, but I don't want to worry about the fact it dropped. I just want amount, so I put it in the absolutes. So the absolutes convert my negative to just positive values. So it was an 85-cent change, a $1.35 change, and it was a 20-cent absolute of negative is a positive. So the total change the stock went through was $2.40. It wasn't an increase or a decrease of $2.40. It was an overall up and down $2.40 total change. So that's what an absolute can describe. The next example, you can read it about Wesley volunteering. I got to be honest with you, who's going to track how many floors they travel in the course of a day? But in a math class, we need to know that information. But it talks about, if you read it, Wesley went from the first floor when he arrived to the 6th floor. And then from the 6th floor, he went down to the 2nd floor. Then he went up to the 4th floor, and then he went down to the 1st floor. So the question doesn't say where did he finish, what was the net change, what was the total change in floors for the whole day. Well, again, I don't care if it was going up or down. I just want the total value. Finished from 6, started at 1, so there's the first change that occurred. It's a positive 5 because we went up 5. I want to add the second change that occurred. The second change, he finished at second floor, started at the 6th, which we can see was a negative 4 floors going down. I don't care that it was 4 down though, I just want to know that it was a 4 floor change, so I want the absolute of it. Next change was from 2 to 4, so the change would have been 4 minus 2, and the last change finished at 1 from 4. So again, it was a 3 floor drop to finish, but I don't care that it was 3 floors negative, so I just want to deal with the fact that that negative 3, I want it as a positive. 3 floors were changed. So there's what that equation becomes. 6 minus 1, he went up 5, which was okay. He then went down 4, but I don't care that it was down, so I want the absolute of it. It was a 4 floor change. Then he went up 2. Don't really care that it was a positive 2. It was just a total of 2. And the last one was down 3, but we just want to know that it was a change of 3. So the total amount of floors, if Wesley kept track of it on a given day, would have been a floor change of 14 floor total change on that day. So absolute values representing a total of something, direction's not important. So that's sort of your introduction to absolutes. Not going to have to worry a lot about that stuff. It's this other information that becomes important. So let's take a look at an absolute function, which is like saying the graph, because this is where most of our focus is on. Well, an absolute value function graph, which is what a function is, well, it's the absolute of a variable. And an absolute tells us that everything is going to be positive. So we're looking at these saying we cannot have a negative part to this graph. So let's take a look. This first example is saying that we have y is equal to f at x. I just took the 2 charts that were in the notes and split them instead of having one big one. The first one, we want to know that y is for the function at x, and the function of x is just x. So our y equals, because that's what f at x is, x. So y is equal to x. So x is negative 3, y is negative 3. X is negative 2, y is negative 2. And that's all our first graph is, saying that f at x is x, so y equals x. So I can graph that. Negative 3 is 3. Negative 3 is negative 3. Negative 2 is negative 2. That's not right. Oh, I'm off a little bit. This scale's off a touch. I apologize. Bummer. It's not what I wanted. Let's just change this up. Sorry, I want to change this to be negative 2 here. Negative 4 there. Negative 6. Negative 8. And negative 10. It's going to happen on all these graphs. Grr. Anyways, we've overcome. Yours should be okay in your booklet. So we have negative 3 is at negative 3, negative 2 is negative 2, negative 1 is negative 1, and so on. So we can create this initial graph. That's the graph we have for y equals x. Y is equal to x. That's our first graph. Well, the second graph now we want to do. Now we go to the absolute. We want the y to be the absolute of the f at x. So we're going to call it g of x because it's a different graph. But really what we're saying is that y equals the absolute of x. So we no longer want y equal to x. we want y to be the absolute of x. Well, that means that we want the absolute of negative 3 or 3. We want the absolute of negative 2 or 2. We want the absolute of negative 1, which is 1. We want the absolute of 0, which is 0. And the absolute of the positives just stays positive. So that's not a big deal. But all of a sudden, when we do the absolutes, these values that were negative, my absolute turns them into positives. So now when I go to graph this, my first point is negative 3, 3. So at negative 3, I'm now at positive 3. Negative 2 is now at positive 2. Negative 1's at 1, 0's at 0. And 1 is now 1, 2 is 2, 3 is 3, and so on. So we end up with a new graph for the absolute graph where y equals the absolute of x. And what happens? Because we want the absolute, all of the y values became positive. Nothing went down into the negative y portion. That's what happens with an absolute graph. The graph that we start with, our initial y equal to x, there's our regular function. As soon as we absolute it, we actually take this negative portion and it gets reflected up to become the positive y values. That's what an absolute graph will do. Nothing will stay negative. That's what we're looking at. We won't have any y values negative for absolute value graphs. Let's take a look at the second one on that page. Again, pause the video and see what we come up with. Give it a try if you want. So what we have here, let's fill in what we know. Negative 3. Our first graph now will be y equal to f at x will equal x squared minus 3. So when we plug a negative 3 in for x, negative 3 squared is 9, minus 3 is 6. When we plug negative 2 in, negative 2 squared is 4, minus 3 is 1. Negative 1 squared is 1 minus 3 is negative 2. 0 squared is 0, minus 3 is negative 3. 1 squared is 1, minus 3 is negative 2. 2 squared is 4, minus 3 is 1. And 3 squared is 9, minus 3 is 6. So there's our f at x graph. We can graph this. Now what do we end up with? Well, it's an x squared. We end up with a parabola because it's a quadratic. So we're at negative 3, 6. We're at negative 2, 1. We're at 0, negative 3. We're at 1, negative 2. My bad. Negative 1 should be at negative 2. Sorry about that. Negative 1 should be at negative 2. And then our 1 should be at negative 2. And our 2 should be at 1. Negative 2 should be at 1 as well. And 3 should be at 6. So we end up with, not surprisingly, with x squared, a parabola. There's our parabola for y equal to x squared minus 3. Well, we're going to do the same thing, but now we're going to do that same thing for y equal to the absolute f at x. So in this case, h at x, because again, it's a different one, different graph, different variable, but y essentially is now the absolute of x squared minus 3. So we're going to plug the same thing in. Negative 3 goes in, still leaves us with a 6, but we want the absolute of 6, which is 6. Negative 2, 4 minus 3 is 1. We want the absolute of 1, which is still a 1. Negative 1 becomes a negative 2. We want the absolute of negative 2 for this graph. So all of a sudden, my negative 1, instead of being negative 2, negative 1 is paired with the 2. 0 absolute of negative 3, which is 3. 1, absolute of negative 2, which is 2. 2 is back to being a 1, which is just 1. 3 squared, subtract 3 is 6 again. So some of the values don't change, but these negative y values, because our y is now absolute, my negative y values became positive y values. So now we graph this one. We have, at negative 3, we have 6. At negative 2, we have 1. At negative 1, we have, oh, it's not negative 2 anymore. Negative 1, we get 2. 0, we have 3. 1, it's not negative 2 anymore. It's back again to being a 2. 2 becomes 1, and 3 is 6. So what's happened? If I create this graph, we end up with well, it's not really a parabola anymore. What's happened, again, is all of this y that was negative reflects and goes up to be positive. So we now have, for our y equal to absolute of x squared minus 3, we have a graph that's only positive and above the x-axis. That's what an absolute is. Part of the graph, both of these situations, part of the graph stayed the same. Even on the previous one. If we take a look at the previous one, part of the graph stayed the same. But when the graph went negative, we had to reflect. When the graph went negative, here, down below, we had to reflect so that it actually became this positive then. That's what an absolute does to a graph. So, here's where you have to start to think a bit. It's a bit of a long video, so bear with me. Piecewise function. Piecewise function is a function that's composed of 2 or more separate functions. So what we end up with, and why we have 2 separate functions, is we now have the f of x portion of our graph, which I showed you on that last graph was what was in blue. The f of x part didn't change. But then we ended up with the absolute portion, which had to change from the original. So we need to identify what piecewise is saying is we need to identify the domain. What part of the x-axis creates the 2 different portions? And what it'll look like is y equals the function if x is greater than, less than. We need to identify the domain. What part of the x-axis gives us what I refer to as the normal part of the graph. But we then have the second part of the graph where y was, now here's that negative to make the absolute positive. Y becomes the absolute part of the graph if x is less than, greater than something. This identifies the absolute or reflected part of the graph that's new. So we need to see what part of the x-axis creates each particular portion. Now the second part to this are what's referred to as invariant points. The invariant points are unchanged points on the graph. So it's what's the part that stayed normal. But the key invariant points are our x-intercepts. And the x-intercepts become very important because the x-intercepts are what I call the bounce points. They're the points where instead of going into the negative portion, it had to bounce to stay positive. So this is what we have to do with Piecewise, is we have to look to see where do we have the normal graph versus the absolute or reflected part of the graph, and what are the bounce points to help us figure out where on the x-axis does each part occur. So it's tricky, not a lot of math, but it's tricky. If we take a look at the two graphs we were talking about, what I need you to do is think about first an x-intercept. Remember, x-intercept occurs wherever y is equal to 0. We've talked about this year with roots and solving quadratics. Well, I don't worry about right now the absolute parts, but if I say that y is equal to x and I want the x-intercept, well, when y equals 0, that means x is equal to 0. So we can see that our x-intercept occurs at y equal to 0, well then x is 0. So at 0, 0, there's the bounce point. We can see that that's where the graph didn't continue down into the negatives. Instead, it bounced at 0, 0 to stay positive. So, Piecewise says that if we want y equal to x, well, y will equal x if, when do we get the normal part of the graph? Well, the normal part of the graph, where y equals x, this is where we have the invariant points, where things haven't changed. Well, that occurs from 0 and up. So y will equal x if x is greater than or equal to 0. That's where we get the normal graph. Well, the second part to this is we get the absolute part, where we had to get the negative of the x. And where does that happen? Well, that happened on this part. This is where this all had to go up. That's the part of the graph that became reflected to make it the absolute. And that happened from 0 on. So we get the negative or the absolute part of the graph where x was less than 0. When x was less than 0, we got this absolute value part of the graph where it had to be reflected. Y equals to x is just what we were looking for, what I think of as the normal part. But y equals negative x, that's the absolute part, because that negative says we're talking the absolute. And the bounce point helps us to create that. So let's take a look at this second one. The first thing we need, let's just focus on the x squared minus 3, and we want the x-intercepts. Well, x-intercepts occur when y equals 0. So 0 equals x squared minus 3. Add 3 to both sides. We get 3 equal to x squared. We want a square root to get the x by itself. So x equals root 3, but because we did the rooting, x is positive or negative root 3. And positive or negative root 3, well, it's 1 and a bit, 1 and something. And we can see on this the x-intercept. Well, we have two x-intercepts where we have root 3 and 0. The other x-intercept is where we had negative root 3 and 0. There's our two intercepts. So at root 3, 1 and a bit, we had our bounce point. And at negative 1 and some, we had our bounce points. Not perfect because I just did a quick sketch, but we can see that those are the points they bounced at. So what Piecewise requires, now that we know where we bounced at, Well, we want to know y equaled x squared minus 3, our normal part, forget the absolute. Y equaled x squared minus 3. Where did the graph stay normal? It stayed normal in these two parts there. This middle part is the part where we had to get the absolute reflected. So that means the normal part of the graph occurred there. This is where the normal part of the graph occurred. And it occurred if x was bigger or equal to root 3. But the graph was also normal in this part. This part didn't change by the absolute, and so it also worked if x was greater than root 3 and when x was less than or equal to negative root 3. At negative root 3 and smaller, we got the normal graph. But to finish it off, that was the one part of the graph. The normal part. Well, y equaled, the absolute, remember, is shown with a negative. We got the absolute part of the graph when? Well, we got that for the values between negative root 3 and root 3. So you go back to domain. When did that happen? That happened for negative root 3 less than x, which was less than root 3. So from negative root 3, we wanted x to be bigger, but we also wanted the x's to be less than root 3. So there's the parts of these graphs that help us. This is tricky. It requires some thinking. Let's take a look at page 6. Be patient. I know it's a long video, but here we go. We want to consider the equation y equals 2x minus 3. Well, what's important with this? Well, we want to graph it, but that x-intercept is the most important part. Y-intercept helps us graph, but the x-intercept, remember, is our bounce point. That's what's key. So when y equals just 2x minus 3, we want for the x-intercept to y to equal 0. So when y equals 0, we get 2x minus 3. Isolate the x. X is 3/2. So our y-intercept is at 3/2, 0. So that tells us for this graph at 3/2 or 1.5, which is about there, that's where we should be getting our bounce point. So at 1.5, we're getting our bounce point. We're hoping. That's our x-intercept. So if I graphed y equals 2x minus 3 without the absolute, well, I can plug -1 in, I get -5. Plug 0 in, get -3. Well, here's our x equal to 3/2. That was kind of important. It's 0. Plug 3 in. 2 times 3 is 6, minus 3 is 3. Plug the 4 in, we get a 5. Well, we can graph that then. So we have -1, -5. We have 0, -3. We have 3/2 and 0. We have 3 and 3. And we have 4 and 5. So we can see that that makes sense because we have a straight line, it's linear. There's our graph. Well, if I do the same thing now with the absolute of 2x minus 3, I'm going to do the same thing, plug -1 in. 2 times -1 is -2, minus 3 is -5. But we want the absolute of -5, which is equal to 5. 0 when you plug in is the absolute of -3, which is just 3. 3/2, plug it in, we get the absolute of 0, which is 0. Plug the 3 in, we get 3. Plug the 4 in, we get 5. And again, because it was the absolute, our negative y's became positive. So if I graph this one now, -1, -5 is now -1, 5. 0, -3 is now 0, 3. 3 halves, 1 1/2, 0 stays the same. My 3 to 3, my 4 to 5. And what do I have? I now have the absolute of the same graph. And again, with the absolute, part of it we can see actually stayed the same. Part of the graph stays the same, but part of the graph went from being in the negatives, the bounce point now made it the absolute part of the graph. So what do? We can write the piecewise. We had the normal graph, 2x minus 3, if x was what? The normal graph occurs here. Here's where the normal graph is. And it occurs from our bounce point and bigger if x is greater than or equal to 3 halves. There's the x values that give us the normal graph. But we have the second piecewise part, the negative or absolute part of that graph. When does that happen? Well, that happened at the bounce point and smaller. So from 3 halves and down, that's where our negative graph reflected to become the positive. So y equaled the negative of 2x minus 3, where x was less than 3 halves. Take note that we always put the inclusion greater than equal to for the main part of the graph, not the absolute. But there's piecewise. We can see the original, see the resultant, and go from there. A couple more. Not going to worry about this one. Let's go to page 8. Y is equal to negative x squared plus 2x plus 8. We have a quadratic. We want to determine the y-intercept and the x-intercept. So we need to figure out the piecewise, but I need the graph first. Again, y-intercept can help us, but the x-intercept, they're the key points because those are our bounce points. And because it's a quadratic, chances are we're going to have multiple bounce points. It's a quadratic parabola. So x-intercept, I go to the original equation. X-intercept tells me that y is equal to 0. So my y will be 0, and now I solve for x. Well, the first thing I need to do is to factor out the negative. X squared minus 2x minus 8. How do I get x-intercepts? Solve a quadratic, factor it. So when I factor this, multiply negative 8, add negative 2, x minus 4, x plus 2. So what will x equal? X will equal 0 if x is 4, and we'll get a value of 0 if x is 0 here, which would be a negative 2. So we have 4 and negative 2 as our bounce points. There's our x-intercepts. Those should be our bounce points for our regular graph to the absolute graph. Now I want to sketch the graph. What's a quick, easy way to sketch the graph? Well, when it's a quadratic, get vertex form. Wow. Blast from the past. Here we go. Again, take our original question, negative x squared plus 2x plus 8. Here we go. Go to vertex form. Bracket the first two and factor out a negative 1 so that we have x squared positive. That's going to become a negative 2x. And we're going to have the plus 8. I need the magic number. Negative 2 divided by 2, but I want that squared. Well, that becomes 1. What did we add to this question? We added a negative 1. So I need to add a positive 1 to counteract that. Now we factor this, negative 1, x minus 1 squared plus 9. There's my vertex form. Why is that helpful? Well, up here the x-intercepts gave us 2 points on the graph, our bounce points, and the vertex form gives us our vertex. Remember, the vertex is now at our p-value, which is 1, and our q-value, which is 9. So at 1, 9, we have our vertex, and we know that our a value is negative 1. It opens down, which makes sense. So there's our parabola through the vertex and through the x-intercepts. So that's y equal to negative x squared plus 2x plus 8. Well, how would I get then the absolute graph? Well, the absolute tells us that our y values can't be negative. So at our bounce points, we're happy with these values, but instead of going into the negatives, now we bounce and reflect these points up. So here's the y equal to absolute negative x squared plus 2x plus 8. Regular quadratic becomes an absolute by taking the y values that are negative and reflecting them to be positive. Now we need piecewise. So piecewise, we want to know y equals negative x squared plus 2x plus 8. When does that happen? But we also want to know y is the absolute or negative of that. Where? Well, where does the graph happen normally? We get the normal graph from negative 2 to 4. So from negative 2 to 4, we have the normal graph. How will we write that? We get the normal graph if, in this case, negative 2 is less than or equal to x, which is less than or equal to 4. There's where we get the normal graph. Where do we get the absolute graph? Well, the absolute graph occurred after we bounced it, so from negative 2 and down, and it also bounced to become the absolute from the x values 4 and up. So we get the absolute graph if x is less than negative 2 and if x is greater than 4. And there's the piecewise for the absolute graph when it's a quadratic. There is lots to think about here. There's some more practice in the booklets. You have my answers in the booklets. This is really about giving it a try. Tough video, I know. Hopefully kind of came along. At this point, my suggestion is to practice. Textbook, couple sets of pages, some with the calculations, and then some with the piecewise. It's tricky. Take a look at the booklet answers for the questions that I didn't do on screen, and see if you can figure those out as well. Have fun with it, folks. It's a tricky one.